Solutions. Solution is the homogeneous mixture of two or more substances of ions and molecules. For example, uh, sodium chloride addition in the water. So in which the sodium chloride, the salt, it's a solute, and the water is the solvent. The solute is the one which is present in the smaller quantity or amount, while the solvent is the one which is present in the greater amount. So when we add sodium chloride into the water, sodium chloride is solute and the water is the solvent. So solute, it forms a homogenized mixture in which both the solute and the solvent, they exist in one phase. In case of sodium chloride, when it get dissolved into it, so it would be passed of the aqueous phase. The water molecules, they get solvated. The sodium ions, they are being surrounded by the OH negative ions of the water, and chloride ions are being surrounded by the H positive ions of the water. So such kind of a mixture which forms a homogenized mixture of two components, it's called the solution. So gaseous molecules, normally they are more soluble, they have more kinetic energy, more miscible in each other. Solids, they also they can form a mixture if they're a mixture of two solids that are miscible in each other such that they can form a single phase. Then we can, it's a solid solution of two solids. So there is a difference between students uh, solution and the colloidal solution. Colloidal solution is actually not the true solution. It's a suspension of colloidal particles, suspended particles in water. The difference is that colloids, they although appear to be homogenized mixture, but they, because of their particles of size, they they do, and their nature, they cannot form a homogenized mixture, but they would be present in the form of suspension. The homogenized mixture will be, they may not be the in the same phase as the solute, as the solvent. For example, in case of sodium chloride, uh, both water and the sodium chloride, when it get dissolved, they would exist in the same phase, so the sodium chloride form homogenized mixture. And when we take a, for example, if sodium chloride forms a homogenized mixture, if we take the water from a sodium chloride solution, so each component, uh, take some water out, it will have this almost same milligrams of sodium chloride per ml of the water. So if you take one increment, two, three, four times, so it would have almost same milligrams per ml. While in case of colloidal suspension, if you take the for example, colloidal suspension of some colloidal clay particles into the water. So if you take out, they will not, they don't have a true homogenized mixture. So you will get variable results when collecting the sample because they don't form homogenized mixture, although they appears to be. So some mixtures, they're called the suspensions that have more larger size, like mud, fresh squeezed orange juice, etc. in water. So they will form also suspensions into the water. So we will be able to realize now the difference between the solution, colloidal suspensions, or other kind of a suspension. It has been normally seen that the solids, they, when they been put into the some solvent, they get dissolve into it at faster rate at initial state, but with the increase in time, the rate of dissolution, it tends to decrease because initially they would have more spaces, more energies, more spaces into the solvent, but with the passage of time they got less spaces to dissolve into it. So with the passage of time, their dissolution rate, it tends to decrease. With respect to the solubility of solutes into the solvent, the solution, it can be divided into different types such as saturated solution, uh, unsaturated solution, and supersaturated solution. The saturated solution is the one where the maximum amount of solute is dissolved into the solvent. So trying to dissolve more results in undissolved solute in the container. While in case of unsaturated solution, uh, less than maximum amount has been dissolved, and the solute can have the ability to dissolve more solution has the ability to dissolve more solute in it, while on the other hand, in case of supersaturated solution, more solute in the solution than normally allowed. So we call this a supersaturated solution. So supersaturated solution can be made. So if we saturated solution, for example, in case of NaCl, if we heat it a bit more and if we add more salt, it can add more solute into it, and ultimately it becomes supersaturated. Now, there are various factors on which the solubility of solutes depends, such as pH, temperature, pressure, nature of solute and the solvent, mixing agitation time and speed, purity of the solvent, and saturation levels. So it depends upon the nature of the solute and the solvent, what kind of a solute it is, whether it's a gaseous solute, liquid solute, solid solute, and what kind of a solvent it is, and what kind of a chemistry the solute and the solvents have, uh, what kind of interactions they would have. Gas molecules normally uh, they are completely soluble in each another because of their maximum randomness, maximum entropy. The molecules in the gas phase are far apart from each other and not interacting strongly with each other in the solutions. Uh, there is a general rule that likes dissolves likes. So substances, materials of the similar nature, they will get dissolved into the same kind of a solvent. For example, polar solvents, they would love to dissolve uh, ionizable solutes. For example, sodium chloride, it can get ionized when it dissolves into the water. So the polar solvents, because they also have charge like water in it, they get dissolved more. So, for example, N-hexane, it's non-polar in character, so its solubility in water would be uh, very low because water is a polar solvent and hexane, it's a non-polar solute if we use hexane as a solute. Now, there is an example in the table of alcohols, alcohol series. So these alcohols, they had a non-polar end and a polar end. The OH groups, it represents the polar character, while the carbon chains, they represent the non-polar character. So if you can see the uh, methanol and its formula and solubility in water. So methanol is miscible in water, but with the increase in carbon chain, you would see the solubility of the these solutes, these alcohols, it tends to decrease into the water because non-polar character it tends to increase. Number of carbons increase कर रहे हैं जिसकी वजह से नॉन पोलर करेक्टर बढ़ रहा है since like dissolves like, so उसके इसके साथ साथ with respect to that solubility in water it tends to decrease. Normally, with the increase in temperature, the solubility of the solids in the liquid solvents it tends to increase uh, at certain extent, with some exceptions. But in case of gaseous molecules, with the increase in temperature, they require high kinetic energy. For example, gas molecules in the liquid or dissolve oxygen into the water. So its solubility would tend to decrease with the increase in high temp with the increase in temperature. While in case of the solid solutes into the water, for example, sodium chloride into the water, so sodium chloride solubility normally tends to increase with the increase in temperature. The reason is obviously with the increase in temperature, the average kinetic energy of the solid molecules increase, and they are freely uh, to go into the solution. Hence, their solubility it tends to increase. Another factor that on which the solubility depends is the pressure. So normally the pressure it has little effect on the solubility of liquid, but in case of gases, uh, the solubility it tends to increase when there would be high pressure, partial pressure of the gas. Also solubility depends on the partial pressure of the gas. For example, if the partial pressure of oxygen in the atmosphere is higher, then the oxygen would get dissolved more into the water. pH is also an important factor on which the solubility of the solutes depends. especially in case of solid solutes when they've been dissolved into the liquid solvents. So because pH can control the charge on the surface of the solute. Ionizable solutes, they may get ionized at certain pH. It depends on their pH and the pK. When the pH of the solution it is greater than uh, normally the 2 units of than that of the pK of the solution, then a solute would be fully negatively charged. While when the pH is less than that of the pK, the solute would be positively charged. So this charge is important with respect to the solubility of the solute. If they have no charge, when pH of the water it is equal to the point of zero charge of the solute, it will get dissolved, then the solute would be 50% ionized and 50% unionized. So there would be no net charge on it. So the pH determines the charges of ionizable species. So it can affect, since we know like dissolves likes, the charge can add to the polarity. So it can affect the solubility. Also, with a change in the pH, number of H positive ions in the water and OH negative ions, they also play important role in the solubility of various uh, species. For example, in case of phenols, they normally have pK more than 9. So they before that they would have positive charge, and when the pH is more than 9, they would require about 9 negative charge. So it can determine the solubilities. So some even organic compounds have polar functional groups where the pH can play an important role in determining their charge, and hence it can helps in the solubility of the various solutes. The solubility of solute also depends on agitation speed and time. Agitation speed should not be so high. For example, in case of gaseous solutes, gas molecules with increase in agitation speeds, they goes into the uh, gas phase rather than being remain into the liquid phase. Example, dissolve oxygen into the water. If we have high agitation speed and more time, then its solubility would tends to decrease. So it depends. There should be some optimum speed we use to calculate optimum agitation time, speed, uh, and in case of solid solutes, when they've been dissolved in the liquid solvents, again the agitation speed and times they matters. It should not be too low. At certain agitation speeds, the solutes they required energy to get dissolved, so agitation speeds can provide energy. So there could be a mass transfer energy into the solution. So with the increase in the speed, it tends to kinetic energy of the molecules tends to increase, and they can easily break down and they get dissolved into the solvent, but it should not be so high. So in the same way, there should be an optimum agitation time for the solutes that can where they can get dissolved into the solvent. So the concentrations, students, they can be represented in various ways. In case of molarity, number of moles of solute dissolved per liter of the solution, or mole fraction, which is the number of moles of a component A divided by the mole fraction of the A plus mole fraction of B. So weight mass, or sometime percent weight, it can be represented. The percent weight can be calculated by mass of the solute over mass of the solution into 10 raised to power 2. So here we have an example where I would like to uh, uh, request you people that you should at least solve this example and similar examples. So solutions can be ppm, ppb solutions. The ppm solution, it normally we use in environmental engineering ppm term. So ppm is the mass of the solute over mass of the solution times per 6, while parts per billion is mass of the solute over mass of the solution into 10 to the power 9. So ppm represents parts per million and ppb represents parts per billion.